While industrial centers pull gigawatts from highly centralized power grids, roughly 770 million people globally live entirely off the transmission network. Operating in these rural regions requires relying on expensive, imported diesel fuel for generators, even when communities are physically surrounded by massive volumes of agricultural waste. Following the harvest in subtropical areas, farmers are left with millions of tons of underutilized crop residue, specifically pigeon pea stalks. These stalks contain 43% cellulose and 29% hemicellulose. This high ligmocellulosic fraction makes the biomass highly reactive and excellent for thermal energy conversion. The established method for converting this solid waste into combustible gas is fixed-bed gasification, a process where fuel descends by gravity through layers of extreme heat. We possess an abundant raw energy supply sitting idle in agricultural fields. However, converting that stock into reliable electricity locally is constrained by rigid hardware architectures. Standard gasifiers are built for a single operational mode. Once constructed, their internal geometry permanently dictates the direction of airflow, locking operators into one specific thermochemical reaction pathway. This diagram compares the two conventional fixed-bed architectures, the downdraft model on the left and the updraft model on the right. In an updraft system, air enters at the bottom, and the resulting producer gas flows upward against the descending biomass. This effectively dries the fuel, but leaves the exiting gas highly contaminated with heavy, engine-destroying tars. The downdraft configuration reverses this mechanics. The gas is forced downward through a high-temperature charbed. The intense heat successfully cracks those heavy tars, but significantly limits the overall cold gas efficiency of the system. Because operators cannot alter airflow direction on the fly, these conventional reactors operate poorly when a batch of biomass has unexpected moisture levels or high ash content. Producing reliable power off the grid requires a single reactor capable of dynamically shifting its internal draft, granting the operator direct control over the thermochemical environment. To eliminate this mechanical rigidity, engineers designed a 50-kilowatt pilot-scale multi-draft fixed-bed gasifier. Built with a two-stage core and heavily insulated with thick alumina refractory lining, the reactor maintains the 1,000 degrees Celsius temperatures required for aggressive oxidation. This schematic details the internal geometry, stacked into 4 distinct chemical zones, drying at the top, descending into pyrolysis, reduction, and finally combustion. Instead of relying on a fixed internal pathway, the system uses movable air nozzles and mechanical valves. This valving network allows operators to physically reroute the draft direction mid-operation. Manipulating where the air enters and how the gas exits controls the temperature profile in the lower zones. This dictates whether the reactor favors the water-gas shift reaction to produce hydrogen or the boudoir reaction to extract carbon monoxide from the charbed. The mechanical valving network acts as a direct dial for syngas chemistry, allowing the reactor to dynamically adapt to the biomass. Even with optimized airflow, raw producer gas carries high concentrations of non-combustible carbon dioxide and heavy hydrocarbons that dilute its energy density. To strip these out, the gasifier utilizes a concentric catalyst chamber filled with calcium oxide, sourced entirely from crushed building demolition waste. Looking at the routing logic, the operator opens valves 5 and 7. This forces the hot downdraft gas out of the main reduction chamber and pushes it directly through the dense catalyst bed. As the gas permeates the demolition waste, a carbonation reaction occurs. The calcium oxide actively binds to and captures the carbon dioxide in situ. Simultaneously, the porous, high-temperature concrete surface provides active sites that thermally crack passing heavy tars into lighter combustible gas molecules. Down at the base, a specialized water tank surrounds the ash grate, scavenging waste heat radiating from the reactor to boil water into steam. Injecting that recovered steam back into the combustion zone triggers a highly aggressive water-gas shift reaction, drastically accelerating hydrogen production. Integrating discarded concrete and recycling thermal exhaust purifies the gas mixture entirely through hardware design, avoiding costly external chemical treatments. To prove the effectiveness of these interventions, researchers ran pigeon pea stalks through all 6 possible gasification draft modes and analyzed the outputs. This chart tracks carbon monoxide output across the test intervals. The downdraft catalyst mode, shown in orange, yields the highest carbon monoxide concentration, proving the demolition waste successfully reforms tars into usable fuel. But the system reaches peak performance in the combined downdraft with steam and catalyst mode. Driven by aggressive steam reforming, hydrogen concentration spikes to a massive 24.25% of the total volume. Because of the intense hydrocarbon cracking inside the reactor, both methane and carbon dioxide levels drop in response to the surging hydrogen. Maximizing these combustible fractions yields a highly energy-dense fuel. The optimized gas achieves a peak lower heating value of 6.87 megajoules per kilogram. Following extraction, this gas is pulled through a cyclone separator and a Venturi scrubber, visible here on the right, to drop out any remaining moisture and microscopic particulates. The final result is a highly combustible, tar-free gas engineered perfectly for immediate engine integration. The final phase connects the purified producer gas directly into the intake manifold of a standard, unmodified spark ignition engine. Because producer gas has lower energy density, the engine governor requires tuning. Setting the air-fuel ratio to 1.6 balances oxygen and guarantees stable combustion. Operating exclusively on pigeon pea gas with zero supplementary gasoline, the engine generates 4.4 kilowatts of power at a 16.8% brake thermal efficiency. These graphs map the emissions of the gasifier-driven engine in red, plotted directly against a standard gasoline baseline in blue. Because the engineered fuel has a low nitrogen profile and burns cleanly, nitrogen oxide emissions plummet. This represents an 85% drop across the load spectrum. Unburned hydrocarbons drop by 78%, and carbon monoxide output shrinks by an average of 80%. Optimizing the thermochemistry at the reactor level yields a highly stable, exceptionally clean mechanical output at the generator. The catalytic steam mode achieves a cold gas efficiency of 87.4%. That high conversion rate translates directly into favorable project economics. By eliminating petroleum and running strictly on local waste pigeon pea stocks costing $117 per ton, the system's operational overhead stays extremely low. When factoring in hardware, fuel, and maintenance, the microgrid achieves a highly competitive levelized cost of electricity of exactly 7 cents per kilowatt-hour. Modeled over a standard operational lifespan, the system generates a net present value of $12,434. This provides an internal rate of return of 26%, heavily outpacing baseline discount rates and establishing strong financial viability for local operators. This entire system operates independent of the central transmission grid, generating power exactly where the fuel is harvested. With precise thermochemical engineering, agricultural residue can bypass the industrial grid completely, turning field waste into cheap, reliable energy independence. The final phase connects purified producer gas directly into the intake of a standard spark ignition engine. Because producer gas has lower energy density, the engine governor requires tuning. Setting the air-fuel ratio to precisely 1.6 balances oxygen intake and guarantees stable combustion. Operating exclusively on pigeon pea gas with zero supplementary gasoline, the engine generates 4.4 kilowatts of electrical power at a 16.8% brake thermal efficiency. These graphs map emissions of the gasifier engine in red against a gasoline baseline in blue. Because the fuel burns cleanly, nitrogen oxide plummets by 85%. Unburned hydrocarbons drop by 78%, and carbon monoxide shrinks by 80%. Optimizing the thermochemistry at the reactor level yields a highly stable, exceptionally clean mechanical output at the generator. The catalytic steam mode achieves a cold gas efficiency of 87.4%. That high conversion rate translates directly into favorable project economics. By eliminating the need for petroleum and running strictly on local waste pigeon pea stocks, costing roughly $117 per ton, the system's operational overhead stays extremely low. Factoring all costs, the microgrid achieves a levelized cost of electricity of 7 cents per kilowatt-hour. The system generates a net present value of $12,434 and an internal rate of return of 26%, establishing strong financial viability for local operators. This entire system operates independent of the central transmission grid, generating power exactly where the fuel is harvested. With precise thermochemical engineering, agricultural residue can bypass the industrial grid completely, turning field waste into cheap, reliable energy independence.